We've all been there. You buy a fresh, puffy bag of potato chips, tear it open, and stare at a container that looks half empty. That gust hitting your face is a deliberate injection of pure nitrogen gas. Blue nitrogen molecules flood the bag, violently pushing oxygen away from the chip. Oxygen causes frying oils to oxidize and go rancid. Nitrogen removes that threat entirely. The gas also provides physical security. Tightly packed molecules act like springs, creating a shock absorber during transit. Manufacturers invest in this gas flushing process to protect a fragile structure that takes months to perfect. To understand why it needs this invisible armor, we have to look at how that structure is built, starting back in the dirt. These potatoes come from specialized contract farms, where every crop follows strict irrigation and fertilizer schedules dictated by corporate agricultural teams. Farmers work toward a specific chemical target, an exceptionally high starch content for maximum crispiness, combined with strictly low natural sugar levels. This split screen shows what happens when that chemistry fails. On the left, a potato with too much sugar caramelizes instantly under high heat, turning dark brown and tasting burnt. On the right, the high-starch potato reaches a perfect golden yellow. When the harvest reaches the factory, it faces an immediate fitness test. Trucks are weighed, and samples undergo hydrometer tests to verify that starch-to-water ratio. This wireframe view shows the final hurdle before processing. Optical scanners look deep inside the potatoes, identifying and rejecting any hidden diseases, internal bruises, or structural flaws. Before a single cut is made, the raw potato must prove it possesses the exact chemical makeup to survive the brutal physics of the factory floor. Once the potatoes are washed and peeled, they hit the slicing blades. These stainless steel rotors spin with enough speed and precision to cut hundreds of pieces every minute. Every single slice must maintain the exact same microscopic thickness to ensure they cook at the same rate. This graph shows the thermodynamic disaster of uneven cuts. In the same vat of oil, a thin slice's internal temperature spikes into a red burn zone, while the thick slice's core stays in this blue raw zone, remaining wet and uncooked. When uniform slices hit the hot oil bath, the transformation is instantaneous. The raw starch reacts, violently bubbling and hardening into a crispy snack. The hot chips travel into a rotating flavor drum where specialized sprinklers coat them with mathematical precision. This ensures an even distribution of seasoning on every piece. The finished chips then pass through an eagle-eye inspection. An array of sensors and cameras analyze the line, dropping any chip that is misshapen or off-color into a rejection chute. This highly controlled process creates millions of identical, structurally perfect chips, but they are incredibly fragile and require immediate protection. At the packing line, automated machines weigh out precise serving sizes of the surviving chips and drop them into foil bags. In the precise millisecond before the heavy heat seal clamps shut, the machinery fires the final protective blast of nitrogen gas. That seal locks in the results of the entire journey. It preserves the golden color, stabilizes the spice ratio, and guards the delicate structural integrity engineered over the previous steps. These pressurized bags are then loaded into boxes, relying on that nitrogen cushion to survive the journey to global supermarkets. When you pop open your next snack and hear that hiss of escaping gas, you are breaking a precise scientific seal that preserves a months-long collaboration between agricultural science and high-speed engineering.